Okay. So if these two coils are in air, then the flux linking the second coil can be increased by bringing this first coil or decreasing the distance between these two coils. If I move this first coil towards this one, then the flux linking the first coil will increase. And also by increasing the number of turns of this coil, I can increase the flux linking the second coil. So mutual inductance is measure of how the flux is getting linked in the second coil due to the current in the first one. To increase the mutual inductance, I can either decrease the distance between these two of them or increase the number of turns. But in the case of a transformer, I have this soft iron core. Okay, on one side we have one coil and this other side is the second coil. But if I take this core and make it big, okay, and have same two coils, okay, and let the mutual inductance in the second case be M2, and let the mutual inductance in the first case will be M1. So M1 and M2, will it be same, different? Which one will be more, which one will be less? Any guess? Mutual inductance is a measure of how the flux is linking the, say, the second coil due to the current in the first one. So will the mutual inductance be same? Understood? No. One of them core is small, the other one the core is large. Say the two coils are at a large distance. So the mutual inductance, the first one and second one, will it be same or different? Or which one will be more? Here I said the two coils are in the air. So when they are in the air, then I said if the distance between the two coils is small, then the mutual inductance is more because more flux will get linked. Okay. So here, what are the mutual inductance? Will it be same or different? Anyone?
Same, sir.
Yeah, it will be same because this core will transmit all the field lines within it. So this core will confine all the field lines inside this core itself. So nothing will go out. That is same case here also. Okay. So here the mutual inductance M1 and M2 are same. This is like saying if you have a say a bulb, okay, and I have a cell here. Okay, so the amount of current flowing this circuit will be same even if this conducting wire is of long length, because the conducting wire is zero resistance, right? Okay, so you want to increase this length of this conducting wire, the current flowing this will not change. Same concept, this magnetic field, since this iron core will conduct the magnetic field lines without any loss. It does not matter whether the thing is large or small. Got it? Okay, so when the coils are present in air, we have to keep them close together because the flux will go everywhere. But once the core is there, it will get confined within the core. So in this case, one way to increase the mutual inductance is to decrease the distance between two of them. Okay. Okay, for an electromagnetic wave, so once I say electromagnetic, you should get this picture. It's traveling in some direction. Okay, so there'll be electric field like this, and magnetic field perpendicular to it. This is magnetic field, and this is the direction of propagation of the wave. So this picture should come immediately to your mind. This is there in NCERT book also, this figure. Okay, so the speed of the electromagnetic wave, what is the symbol? Anyone? Speed of EM wave, what is the symbol? And this value is 3 into 10 raised to 8 meter per second in vacuum. So light is also electromagnetic wave. So what is speed of, or I can say C of X-ray compared to speed of light? Which one is more? Huh?
Same, sir, both.
Yeah, both are same. So the speed will not change because of The difference in X-ray and light is frequency is different and also wavelength is different. Frequency is different and also wavelength is different for X-ray and light, but the speed is same. Speed is mu into lambda. So for X-ray, lambda is more compared to light. Sorry, frequency is more compared to light. For X-ray, the frequency is more compared to the light. So lambda will be less, such that the product of mu into lambda is same for both X-ray and light. So similarly, any electromagnetic wave, take a radio wave, microwave, gamma rays, millimeter waves, whatever it is, speed is same, but speed will change from medium to medium. Suppose change to different medium, say glass, then the speed will be different. So speed is given as 1 by square root of mu to epsilon. Okay, for vacuum it is 1 by square root of mu naught epsilon naught. That's equal to 3 into 10 raised to 8. When I go to a different medium, mu naught will become mu and epsilon will become epsilon. So it will be different from mu naught. So the speed will change because of the medium. So in that second, what is chosen medium? Again, the speed of X-ray and light or any other electromagnetic will be same. So, right. So how many of you want to continue further? So right now, yeah. Akshay wants to continue. What I think
I'm okay, sir.
okay. And
Sir, you can continue, sir.
who wants to quit? Nobody.
No one, sir.
Okay. Right, because fine. So what time is until what time I can go? Right now it's 10:05. Okay, fine. So Biot-Savart law, it gives magnetic field to your current element, right? Because the simplest source of a magnetic field is current element. So Biot-Savart law gives a magnetic field dB to the current element ideal. So this is given as proportionally constant is mu naught by 4 pi ideal cross r cap by r square. Okay, so ideal curve r cap will give the direction of the magnetic field. So using this formula, this is the experimental formula. Okay, these are accepted. Using this, I can find magnetic field via circular current along the axis. Okay, so this derivation is there in NCRT. So you should know how to get this relation or the formula. So to do this derivation, we have to choose two elements diametrically opposite. So we choose this current is in this direction. So ideal here is this way. Okay, ideal here is this way. So because this one, the magnetic field at this point P, this is ideal, right? And this is R cap is this is R cap. R cap. And ideally say at this point it is out of the plane of the paper. So ideally cross this one will be in this direction. So this is the direction of the force due to this element at the top. Okay. Similarly, if I take this element which is diametrically opposite, this is the R cap of this element at the bottom. So this will be perpendicular to this one. Because here the direction of the current is cross. Okay, so this is a circular loop which is perpendicular to this plane of the paper. So if I take the topmost element, the direction of the current will be out of the plane of paper for this chosen anti-clockwise direction of the current. And if I take the element at the bottom, the direction of the current will be cross going inside. So for this cross direction of the current and this R cap in this direction, the direction of force will be ideal cross R cap. So that will be ideal cross R cap. So inside this one. Yeah, so it should be this one. Okay, so since the diametric of these two forces are equal, so the x component of this force, which will be along the axis, this will add. So df cos, if I take that angle properly, so if I take this angle as, so this component will add, but the vertical component, one due to this one will be like this, and this component with the bottom one will be like this. So the vertical components will cancel. So the magnetic field is pair of this current element is towards along the axis and towards right. So similarly, we take the second pair here and here. The same thing happen. This will give a magnetic field in this direction, but the perpendicular components will cancel. So this way we can derive that relation. This is chapter number 4. Circular current loop. This one. Magnetic field area, circular current along the axis. So this is the coil. So I said on the top one, the current is coming out. So it will be a dot. And the bottom element will be inwards because of the force in one. But the magnetic field, one of them will be this way, the other will be here. So if you take the pair, only the component along the axis will add. And this angle they have taken as theta. This is theta. Okay. So this is between the horizontal and the normal to this one. So between vertical and the, so this angle is theta. So this angle is theta, which is same as, so this angle is basically between the vertical and this radial line. So similarly between the horizontal and the line perpendicular to this radial line, which is this one. So this angle should also be theta. That's what they have done. Okay, so that theta will, so angle between two lines is theta. Then the angle between the perpendicular is also theta. If I take a perpendicular to this first line, that is vertical here. Okay, and this second line, I take a perpendicular this way. Okay, so this is the normal here, this is the normal. So this angle is also theta. Okay, that's all used here. This theta is between this vertical and the radial direction. So perpendicular to the vertical is horizontal direction, and perpendicular to this radial is this direction, because DF is perpendicular to R cap and also ideal. So the DF direction is perpendicular to R cap. So the angle between these two perpendiculars is also theta. So just go through this derivation and get this result for a magnetic field along the axis of the circular loop of current. Okay, so in this, if I put x equal to 0, I get the magnetic field at this center point. And for an electric dipole placed in its uniform electric field, the expression for torque, what is torque? P cross E. Okay, so that derivation you have to know. Torque on a dipole in external electric field, uniform electric field is P cross E. Okay, so this is there in the book. So basically this comes from force into the perpendicular distance. Force is Q into E, and the perpendicular distance will come out to A, I think sine theta. Okay, this is on place charge. So the minus charge, then it is the same torque. So it will become 2 times this one. So Q into 2A will combine as P. So it will become P sine theta, which is P cross E. Because A cross B is A into B into sine theta. Okay, so this derivation is there in NCRT, just go through that. Okay, the basic idea is torque is force into the perpendicular distance. So in this case, the perpendicular distance will become A sine theta, where A is the distance, 2A is the distance between minus Q and plus Q. So torque is above the center point, so this distance is A. So the perpendicular distance will become A sine theta. Okay, so the torque will become force Q into A sine theta, and two of them are there, plus Q and minus Q, and both the torques in the same direction, so they'll add up to give me 2 factor. And I can combine Q and 2A as P. This is the definition of the electric dipole moment. P is the charge into the separation between them. So this derivation and equipotential surfaces. What's an equipotential surface? Chapter number 2. First, you have to draw the field lines, right? Field lines is a line or a curve which is tangent to all the electric fields. If I take a point charge, for example, positive point charge Q. Okay, because of symmetry, the electric field lines will look like this. But as you go far away, the thing will drop down as 1 by r square, because electric field goes as K into Q by r square. So you drop down. So to get a field line, I just have to draw a curve which is touching all these field vectors. So the field line for a point charge will look like this. To get the electric field, I have to go to any point and draw a tangent. And to get the direction of the electric field, I put a direction on the field line. So these are the field lines. So there is a field line like this. Field line like this. So you can see close to this point charge, the density of the field lines, that is number of field lines causing a particular this thing, will be more. So if you take the same area at outwards, the density will drop. So if electric field magnitude is more, means the length of the vector will be more. In terms of field lines, the density of the lines will be more. Okay, here the density of the field lines is more. Here, as I go out, the density of the field lines is dropping down. Okay, another thing is the concept of equipotential surface. Equipotential surface means the potential, all the points on the surface is constant. Okay, field lines are lines, which are, or in general, it can be curves. Equipotential surface are surfaces. In this case, the surface will be a spherical surface. Okay, so here in this particular point charge case, the equipotential surface will look like this: spherical shells centered around the point charge. And the rule for drawing this equipotential surfaces, I have to draw it equal interval. Suppose this is at 2 volts, and the second surface I draw 2 at 4 volts. So the inner one should be, or I can say the potential is more as you go in, right? Yeah, if we go out, the potential will decrease. So I have to draw it the other way around. So inside the potential will be more, say we make it 20 volts. As you go, the potential will go down 18 volts because potential is K into Q by R. As I go, the potential should go. So next sequence will be at 16 volts. So the inner one, next one will be at 22 volts. So that is the rule. So for this particular case, so if we follow this rule and draw the equipotential surface inside the equipotential surface will be nearby, outside the distance between these two will increase for the same potential difference. The distance between two equipotential surface from here to here will be less, but here will be more. In other words, I can say electric field. So these are two ways of showing the sign of the magnitude of the electric field. One, the length of the electric field is vector is more. Not only the field lines are densely packed, not only the equipotential surface are closer to will be close. If the electric field is weak, means the equipotential surface is far away. Yeah. See, here's a positive charge. So if they draw it properly, the density of the field lines here it's more. As I go, the distance between the two equipotential surfaces increasing. Okay. See here the potential drop from here to here is 2 volts, right? So that means the work done to move from here to here is 2 volts, and the work done to move from here to here is, but for a shorter distance, 2 volts, because here the electric field strength is more. The work done is F dot ds. So this is nothing but Q into E into dot ds. So the electric field is strong means for a shorter distance, I'll get the same potential difference. So here for a drop of 2 volts, since the electric field here is weak, I have to travel a larger distance to get the same drop of 2 volts. But if I go inside to get the same drop of 2 volts, since the electric field is strong, this ds is less. Okay, and also electric field is related to the potential as the gradient, right? dV by dr minus. So if the electric field is more means for the given potential difference of say 2 volts, this dr should be less. For E to be more for same delta V, the dr should be less. So here the electric field is stronger inside, so the dr, the distance I have to cover to get the same drop should be less compared to the outer one. Here the dr should be more. So to conclude, I will say when the electric field strength is increasing, if I represent electric field as a vector, the length of the vector will increase. And if I represent as field lines, the density of the field lines will be more, because here the density of the field line is more, the electric field is more compared to the outer region. And also the equipotential surface will be closely packed if the electric field is strong. Here on the inside, the equipotential are nearby. As you go out, the electric field lines will, sorry, the equipotential surface will become far away. And the rule for drawing equipotential surface, I have to draw equal intervals. So the drop from here to here, if it is 3 volts, the same drop will be from here to here. But here the distance will be less because the electric field strength is more. Okay, to get the electric field strength more, I should have smaller dr for the same fixed dV. Okay. So here the potential is same everywhere. So that's why the density of the field lines is not changing, it is constant. just like between capacitor plates, between two capacitors, the electric field is uniform. So the electric field lines, the distance between them will be uniform, it will not change. But if you take this sort of a dipole, so here you can see the field, here they are equipotential surfaces. They are close nearby, so the electric field is more here. As you go farther away, the electric field lines are, so the equipotential surfaces are far away. So here the electric field is less. Okay, we will continue tomorrow. I think we can close now. Is it okay?
Okay, sir.
Yeah, because tomorrow we have
Okay, sir.
tomorrow we have full day and organize my thoughts because almost whatever is required I already told in the previous test also. So I just make the list of concepts we have to know. Okay, and then I'll discuss based on that. Yeah.
Okay, sir.
Okay, sir.
Yeah. Okay. Good night.
Thank you, sir.
Yeah.
Thank you, sir.
Thank you, sir. Good night, sir.
Good night.